Hi everyone, welcome back to day 9 of Advent of Code, Disk Fragmenter. It's a very interesting question, and the challenge is going to be super fun to solve. So, here, the story aside, in which we are still looking for the chief, and there's some cool stuff happening, we have to help one of these amphipods that needs help with his computer in defragmenting the disk. So what we get is a disk map, something like this, and there's a meaning behind these numbers. So what it is like the first part is the block number of blocks of the file, and the second part is the number of free spaces after that block of the file, and they're in pairs like these two and these two. So two blocks, then three free spaces, then three blocks, then three free spaces, then one block, then three free spaces, and so on. In the end, you will have either free spaces or another block. Like suppose this doesn't have its pair, it means it's just two blocks and there is no free spaces. At least in the examples, they have not mentioned anything with free spaces at the end. So I have a feeling it'll we'll take that into consideration when we write the code. So then what we have to do now is first we have to bring it in this format where if there are two blocks and then three free spaces, we have to represent it in a certain way. But how we do that is the first pair is the 0th id, like in an array. This pair is the 0th id, this is the first id, the id of this pair is basically 1, and so on. So what we have to do is we have to bring this to this format where we say id 0 has one block of code with one block of the file with two free spaces, and then the id1 of the id1 has three blocks of the file and four free spaces. They have taken this from here, right? Yes, it's from here. So it's one block, two free spaces, three blocks, four free spaces, and then five blocks. So IDs are 1, 2, and 3. So yeah, that's what we have to do. So now they've explained it with this example that they gave us here. With this example, we'll get something like this because it starts with two blocks and three free spaces. And then and in the end it's 888899 because there are four blocks and zero free spaces, and finally two blocks. So what we have to do after getting to this stage is they are taking the easier example again. So for the first one, what we have to do is starting from the end, we are supposed to move these blocks to whatever free spaces exist in the starting, so that the end is ultimately the end only has free spaces. So we start with this, move it to the first free slot, like in this step. Then we would take this and then we move it to this place. It becomes like this, and we keep going on till we reach this state. Similarly, for our example here, we get this, from which we get this. So now after we have done all this, after we finally brought it to this state, we have to find the checksum. In how we find the checksum is we multiply this, whatever number is there in this, with the index, like the position. So it's 0 cross 0 for the 0, then it's 1 because the position is 1 cross 0, whatever value is there, and we go on and we sum that up. Whatever we get as the sum is the answer. So let's try that. I mean, it took some time to understand this and read this, so I think I've tried to tell whatever we have to do here in the easiest way, but it still might be very confusing. Anyway, let's try this now. Okay, so we've got the code here. So what we're doing is we're processing the input, and this time we are not doing the usual processing. We are going directly to what was required of us to do. We are making a memory map, and why this is also something that I'll have to explain. So suppose we have 1, 2, 3, 4, 5. In this case, it's easy because we have one block of memory and 2 free spaces, then 3 blocks of memory and 4 free spaces, and then this was supposed to be 2. This was supposed to be 0, right? Am I messing up already? Yes. So this and yeah, so it's kind of hard to remember all this. 1, 2, 3, 4, 5 becomes something like this: 0, 1, 2. But think about it, as we go on and on, you'll get 3, and then you'll get 4, and then you'll get 5, and then you'll get 6. Till it's single digits, it's all good. But at some point, you'll get something like 10 with 3 blocks of spaces after that. But this 10 if we are using it in a string, right, we will see that as 2 different digits, which will not work for us, and keeping track of index that way will become a little hard. So we are making a form of our own array by using this map, where we will be like index of, let's say, 19 will be at index 19 we will have value 10. Similarly, if we did it on a string where we were like string of 19, like in index 19, we will get 1 or something. So just as an example, I'm saying it, just don't start counting the position of this literally. But yeah, so that is the problem, that we will start getting 2-digit stuff, and that will cause an issue. So I've made this memory map, and in this memory map, first we're checking if it is a block or not, and we are like basically alternating between if it's a block or it's not a block. We are keeping track of the ID, like I said. Like the question said, the ID starts from 0, and we are keeping track of index because we are making our own sort of an array, right? So we need an index. So now we are running to a double for loop. Definitely could be more better. I mean, there can be a more efficient way to do this. I feel like just this double for loop with so many conditions itself will definitely make our main input take a lot of time. But anyway, we'll see about the efficiency after this, once we have some solution at hand. So we are keeping the size, which means size of the block or size of the free space in a variable. And while the size is less, I mean while our j is less than the size, we are adding it to our memory map, which means if the size is suppose 3, so you're doing 1, 1, 1, and if the size is 4 of the free space, we are doing dot 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 dot. Yeah, so that's what it is. And then we are alternating that this is now a block and now this is a free space. And if it is not a block, then we are increasing the ID, because this is 0 till here, and then we increase it to 1 till here. So that's how we go on. So this time the process input itself is a little involved. Then we are defragmenting the map. I mean, the question is disk fragmentation or disk fragment, but we defragment our disk so that we get like contiguous free spaces of memory. At least that's what I remember. So that's what this is. We are defragmenting the map. What we're doing in this is basically the ask of our question today, the challenge, which is to move whatever is in the end to whatever is in the free spaces behind us. So for that, what we are doing is we have the ith and the j. We are using this thing which is called a double pointer method. How that works is we have suppose 1, 2, 3, 4, 5, 6, 7, and I'll put some dots just so that it's readable. 8, 9. Okay, so here we will have one pointer looking at this and one pointer looking at this and one pointer looking at this. So what our logic is doing right now is, suppose we will start by looking for a free space. Let's put one here so that I don't have to go very far to do that. We are starting by looking for the free space, and this is the ith pointer and this is the jth pointer. So we start by looking for the free space, so we go all the way here, and then we find that okay, this is a free space, this is what we need, and then this starts at the last thing. And if this is not a free space, then we are ready with this as well. That's what this condition is checking. If the I pointer is not pointing at a dot, then keep incrementing it till you get to the dot. Otherwise, check if the jth pointer is pointing at a number instead of a dot. If it is pointing at a dot, which is a free space, then keep going backwards till you find some position where there is no dots. So we find 9, and then we replace this with 9 and then this with a dot. So this becomes a dot, this becomes a 9, and then we go through this again, and this time this is not pointing at a free space, so we keep incrementing it till it reaches this. But unfortunately J is pointing at a dot, so we'll keep reducing it till it reaches this. Then again we'll swap between this and this, and so it goes on. We get a sort of a thing like this, which is an array. Think about it as an array, which is also telling us that this index holds this value, this index holds this value, and so on. To verify this, instead of having it as a map, I printed it as a string, for which I use this method, which is basically converting it to a string. Okay, but that is just to validate. And then we have this checksum method, which is just doing literally just going to the 0th position. Taking the 0th position, the 0th value, multiplying it and adding it sum of products, and we get this. Here this is the sum of products. We get this, we return it, and fortunately we're getting the right answer as per the sample input. Now we should try it with the actual input and see what we get. I think this will take some time. What? That was very fast. I'm happy to see that, but this is definitely not efficient. Okay, before I submit, I should share this screen. Okay, let's submit. Great. Okay, that was actually very easy. Don't become too happy and jinx the second part. Now let's do the second part. Oh my god, after a lot of hard work and almost, I don't even know how many hours of this and how many different versions of this, I finally got the solution to it. It might not be the best solution, but I'll tell you my thought process, and I'm definitely going to look up how other people have done this. This is a good challenge. So basically, I have used a linked list, the idea of linked list here, because I wanted to be a contiguous memory, and even to track it, I've used the same. So there's two maps that I'm using. One is the memory map and one is the size map. The rest is the same. There is block, index, so everything. So the memory map is basically an object which keeps track of the block name. It could be the ID or it can be a dot. It keeps track of the size and the next. So this is how linked list is, right? The address for the next one is kept here. I'm keeping the index there. So it keeps a track of all that. And then if it is a block, then we also keep track of the size and the original index. Because in the linked list, there's no such thing as an index, but we need to keep track of the original index because we only have to swap the positions of the more like the blocks which are ahead to the ones which are behind. So then we are just checking if it is a block, then we will not increment the ID, and if it is not a block, we'll increment it. Index is the address. Basically, I'm keeping a way to remember the address, because in C++ and C you could create memory locations and then give that address to your next pointer, but here we are just giving we are making our own address basically. Okay, and then memory map of the last linked list, I mean the last linked list item will not have a next, so we're making that null. By default it will just make it index +1. And finally we're returning these four things: one memory map, size map, the number of IDs that we have, and the total number of elements, so that if we have to add to this linked list, we can continue from here. Defragment map, we are going through the linked list here. We are going through each element in the linked list. We are keeping a track of the size which is required. How do we start this? Okay, so the max ID is the last element that we had the ID, like we have 0 to 9, so this will be 9. We start with 9, and my size required for 9, we remember it from this size map, the size and the index. And the maximum index that we can swap with for our element is the max index. We are checking if it has already been swapped so that we can break from the loop. We are keeping a track of the index and the previous index so that we can change the addresses. And now the first condition is if we find a block that is a free space and the size of it is greater than the size which we require, and the index which we are going to swap is less than the maximum index, and if it is not swapped, then we will swap it. We'll create a new node, place it there, put the next index to whatever we have created, I mean whatever was existing before. And yeah, I'm finding it hard to explain this completely, but I'll try again. So we have in our map, we're keeping a track of all the free spaces, so we're reducing the size of that free space, and then we're creating a new node. In the new node, we are now the new element, the element that we are swapping from somewhere ahead, we are putting that in this new node, and the size which it requires. This is to keep track of think of it as a string, so in that how many characters are there of this, it's like that. And then the next index, so whatever it was originally pointing to, here the free space, whatever it was pointing to, we'll point to that. And the previous, whatever the previous was, before this linked list item, that will point to this node now. And then we'll mark this as swapped, and then the size will increase because the number of items in the linked list have increased. Actually, the number of items will remain the same, but we are removing one node, and that address is of no use to us. So we are adding this. The number of addresses, or the last address that we are tracking, that is the size. Should rename it to something better than that. Then if we have swapped it, we still have to remove the element which is existing ahead in our line. I have a good thing for this. Yeah, so this is the original. So now this, after 2 we have 3 free spaces. These are the dots. So we're moving this 9 2 to this place, so it becomes 0 2 9 2 and dot 1, because only one space is remaining, but we still have to remove this 9 2. So for this 9 2 we are going through each element of the linked list, and when we finally reach this 9 2, we make that a free space, and then we are keeping track of the previous index and the index. But now there is one more problem. Suppose this becomes dot 0 and dot 2. These two things are actually the same thing. I mean, it'll be harder for us to track it if they are existing separately. Suppose this was dot 3 and this was dot 2. This is actually a space of 5, and if we don't combine it into one single entity, then we'll not be able to track it. We'll be able to track it as dot 3 and dot 5 separately. Dot 3 and dot 2. Here it's 0, so it doesn't matter so much, but there are chances. Like suppose we swap the 7 3 out from here and put it somewhere else, it becomes dot 1 dot 3 dot 1. So there is like 5 spaces here, but we are keeping track of it separately, right? So this part will combine it into a single space. Yeah, after that, once we got the map, the length was no more required in this part, but I've not removed it. We do the checksum by going through each element of our linked list and keeping a track of the position. So 0 2, which means it has 2 positions, 0 and 1. Then 9 2, then that means it's 2 and 3. Like that we keep going. This is the position, this is the total, and this is the index, which is the address of our node. We keep going that way. Now after blabbering so much, let's see if my code actually works. Oh god, this is so messed up. Yeah, this is definitely very, very slow. Let's see if this is right. Great. Man, that was a lot of hard work. I think I've spent 3 hours in just the second part, which is bad, but it took me a lot of time to come up with an idea, and I've gone through multiple iterations of this and some previous ideas. Oh yeah, I've deleted like 2 files before doing this. I think I'll remove that part of the video so that it's not like too much nonsense for you guys. Yeah, so you will have a shorter video to watch and get a better explanation. All right. See you on the next day. Bye.